Okay, now let's try to define a metric on a function space. Okay, so we're talking about the function space CG omega. They are open sets in the complex plane. And first, we need a proposition. If G is open in C, then there is a sequence Kn of compact subsets of G such that G is the union of Kn and from 1 to infinity. Okay, so every open set can be written as a union of a sequence of a compact set. Okay. Moreover, the set Kn can be chosen to satisfy the following conditions. So there are three conditions. Condition A, each Kn, each compact set is contained in the interior part of the next compact set. So one is contained in the next one, not just the next one, the interior part of the next one. B, K in G and K compact. So this Kn is related to G by this condition. And for any arbitrary compact set K, so K is a compact subset of G, any compact set, it implies K is a subset of such one of Kn for some index n. C, every component of C infinity extended complex plane without Kn. Every component of this C infinity minus Kn contains a component of C infinity without G. Okay, so that's three additional conditions. All right, now let's see the proof. This proof is actually one of a possible construction. We are going to really construct this sequence of Kn, and we are going to show that our construction satisfy those three conditions. Okay, so for each positive integer, let Kn be the set of Z such that the modulus of Z is less than or equal to n, intersect the set of Z such that the distance between Z and the C minus G, the complement of G, is greater than or equal to 1 over n. Okay, so recall that to be a compact set in the Euclidean space, finite dimensional Euclidean space. To be a compact set, it means it's bounded and closed. Bounded, it can be covered by some disk, closed disk. So this first condition implies it's bounded. And it's a closed. You see here, we always choose greater than or equal to or less than or equal to. Those conditions will give us closed set. Bounded closed, this will imply this Kn is a compact set. Okay? Since Kn is bounded, this comes from the first one, and it is the intersection of two closed subsets of C. Okay, so whenever you put less than or equal or greater than or equal, it represents a closed set. So it is the intersection of two closed sets. We know that the finite intersection of closed set is still closed. So Kn is bounded and closed. So say Kn is compact. Kn is always compact, right? Okay. And so we get the first one. And let's see how do we get G is equal to the union of Kn. You see, by the second condition, Z is away from the complement of G. The distance between Z and C minus G, the complement of G, is greater than 1 over n, so it's away from G. So this implies Kn is a subset of G. Kn is always a subset of G. Okay, and for every Z inside G, of course, Z is not inside the C without G. Inside G, then this is not in the complement. If it's not complement, if it's not in the complement, the distance between Z and W is strictly greater than 0 for all W in C without G. Okay, it's not inside it, so the distance is always greater than it. And we have to claim it's not just greater than 0, it is greater than some fixed number. You see here, this condition, it's uniformly away from the complement. Why? Okay, we are going to show that. If there is a sequence Wn of C minus G, if there's a sequence Wn from this complement such that the limit n approaches infinity, the distance between Z and the Wn is 0. If we have such limit, then we know that Z is a limit point of this C minus G. Z is going to be a limit point. But C minus G, G is open, C minus G is closed. Closed set contains all the limit points. So C minus G contains Z, which is a contradiction. Because we assume Z is not inside the C minus G. Then this contradiction comes from this assumption. You assume there is a sequence Wn of a C minus G such that the limit is 0. The limit of distance is 0. Hence, what we get? we know that the infimum of distance between z and the w belongs to c minus g. It cannot be 0. It's strictly greater than 0. It is strictly greater than 0. Okay? So actually this is a condition, and this infimum is defined to be the distance between z and the c minus w. Remember, when you have a point and a set, then the distance between a point and a set is the infimum of the distance between z and a. A belongs to set A. So this is the definition of a distance between a point and a set. And from this argument, we know that if A is closed and z is not inside A, then the distance between z and A is strictly greater than 0. This infimum is greater than 0. The infimum is going to be greater. So that's one condition. Infimum is greater than 0. So, okay, this is the condition we have. Then there is an integer n1 such that the distance between z and c minus g is greater than 1 over n. N is 1 over n1. N is very, very big. When n is very, very big, 1 over n will be small. When n is big enough, this 1 over n1 will be small enough, so it can be less than the distance. Okay, so you have to know this distance is strictly positive, not greater than or equal to. Okay, and also there is an integer n2 such that the modulus of z is less than n2, right? You just choose n2 as an integer part of a modulus of z and plus 1, right? So here you can let n2 be the greatest integer part, the greatest integer function, and plus 1. It will be definitely greater than it. All right? Okay, whatever. This is just one way. Okay, then we choose n to be n1 plus n2. By this choice, n is greater than n1, n is greater than n2. Then z will belong to this kn. The distance is greater than 1 over n, and the modulus is less than capital N, less than this n. So z belongs to kn. So where did we start? We start, you see, here. We start for every z in G, we go through those process, we know that there is n such that z belongs to kn. Hence, we have G to be the union of kn, and from 1 to infinity. Right? All the kn are the subset. Every element belongs to one of those kn. So the G is equal to the union of kn. All right. So here, this is the vigorous proof of the first condition. We want to get this condition. This part is skipped by the textbook, so I'm trying to provide the complete proof. Okay, next, let's verify our construction satisfy those 3 conditions. Okay, we verify three conditions. A, okay, I'm going to copy it here. We want to verify Kn is inside the interior part of a Kn plus 1. The interior part of a Kn plus 1 is actually z, modulus of z is less than n plus 1. This is open. Without the equal sign, it's open. And this is kn plus 1, so it's less than n plus 1. Intersect z, the distance between z and c minus g is greater than 1 over n plus 1. Okay, so this is the interior part. And of course, kn, let me copy it. Kn modulus of z is less than n, intersect the distance between z and the cg minus c is distance between z and the g minus c minus g is greater than or equal to 1 over n. Greater than or equal to 1 over n, of course, is greater than 1 over n plus 1. Here, less than n, of course, is less than n plus 1. So clearly, kn belongs to, is a subset of an interior part of a kn plus 1. Kn is an interior part of kn plus 1. Okay? Okay. And this is a first verification. From this verification, we also have one property. G is the union of Kn. G is also the union of an interior part of Kn. Right? Each interior part belongs to the Kn, so this is a subset of this union. And each Kn belongs to the interior part of Kn plus 1, so this part is a subset of the next one, so they equal to each other. Okay? So Kn is a compact set, but the interior part of Kn is always an open set. All right? So second condition. A compact subset K of G it implies K belongs to Kn for some integer n. Okay, so we're going to show this. Okay, so K is a subset of G, and G is the union of interior part of Kn. Okay, so compact set. What is the definition of compact set? Every open cover has a finite subcover. Okay, so here the interior part of a Kn n from 1 to infinity is an open cover of K. Of course, it's an open cover, right? K is a subset of those unions, so it's open cover. Then, by the definition, of compactness of K, there is a finite subcover. Like, for example, we say interior part of a Kn1, interior part of a Kn whatever m of K with n1 less than n2 less than nm. Okay, so we just pick up some finite subcover. And once we have n1 less than n2 less than n3 less than nm, the interior part of a Kn1, it is contained in the Kn1. Interior part is a subset. And it is inside the Kn1 plus 1, and it is inside the interior part of a Kn2. And eventually it is contained in the interior part of a Knm. Okay, so actually I want to say that this open cover element belongs to next one, belongs to next one, belongs to next one. They are all subset of the last one. So the interior part of a Knm itself covers K. You don't need a finite subcover. You need a single subcover. It's just because of this, where is it? Yeah, this condition, because this condition, You only need one open set to cover K. And interior part, that's K belong to the interior part of a K and M, and it's a subset of K and M. So K is a subset of K and M. Okay, so we proved the condition B. Okay, see it? Okay, part C. Part C is very long. It says every component, connected component, every component of C infinity minus Kn contains a component of C infinity minus G. All right. Okay, let's try to see. We're going to show this. We're going to show this condition. Component. There are two types of component. One is called a bounded component. One is the unbounded component. Okay. So first, for the unbounded component, C infinity minus Kn. For the unbounded component, C infinity minus Kn. Kn is a subset of G, and of course, C infinity minus Kn contains the C infinity minus G. And the unbounded component definitely contains infinity. Unbounded component of C infinity minus G must contain infinity. Infinity becomes an element in the C infinity. Okay, so it contains the component of C infinity minus G. Which component? It contains a component C infinity minus G, which contains infinity. Contains infinity. Okay, so here there's actually the argument. It's not that straightforward. So first of all, you have to assume unbounded component is there. If the unbounded component, this one, of course, unbounded component always there. This one, it may not contain the unbounded component. Okay? So for example, let's see. We just use one example. It's not that obvious. So for example, we choose G to be set of Z such that modulus of Z is greater than 1. The exterior part. Okay, so G itself is unbounded. If you get C minus G, it becomes a closed subset. Okay, the closed disk interior part. But if you use C infinity minus G, you will see it is closed part union infinity. Infinity is an isolated point. It is not contained in G. Then, in this case, the component of C infinity minus G, which contains infinity, the component of C infinity minus G, which contains infinity, is just this element, singleton, the set of one element. And C infinity minus Kn is outside of a closed disk with radius n, of course, it is contained in the component, unbounded component of C infinity minus Kn. Okay, so this infinity is always there. This infinity is always there. But when you talk about the component of C infinity minus G, this may just contain one element. It's not just, you imagine it's always infinity with a neighborhood. No, it's not that way. Okay? Okay, so that's I'm not saying I'm wrong. I'm just saying there's some subtle case, a special weird case when you have this situation. All right? Okay, so unbounded component must contain the component of C infinity minus G, which contains infinity. The most degenerate case means you only contain C infinity. All right? So this is an unbounded case. For the bounded component of C infinity minus Kn. For the bounded component, C infinity minus Kn. What is a Kn? Kn is Z modulus less than or equal to n intersect Z distance between Z and the C minus G is greater than or equal to 1 over n. This case. So the set, this set is contained in the unbounded component of C infinity minus Kn. It's not inside the Kn, so it's in the complement. And it is unbounded connected, unbounded and connected, so it is in the unbounded component of a C infinity minus K. And now we're talking about the bounded component of a C infinity minus K. Then all bounded component of C infinity minus Kn is contained in contained in where? Here. Contained in this closed disk. Right? Because outside it is definitely contained in the unbounded component. Then we're talking about the bounded, so it has to be inside the open disk. It is inside the open disk, but it's not belong to K. It means it satisfies first one, but not satisfies second one. Right? So for any point, for any point Z in let me see. For any point Z inside this component, that's the bounded component, let's call it D. Inside this component D, there is a W in the C minus G such that the condition, what condition? Now this condition is not satisfied. The distance between Z and the W is going to be less than 1 over n. Okay, the distance fails. The distance condition fails. So ZW, the distance is less than 1 over n. Okay, so from z you can find a w. You can find a w. But for the whole set z such that distance between z and the w less than 1 over n, this whole set fails the second condition. So this whole set belongs to the C infinity minus kn. I just say it fails the kn, the definition k. Kn must be greater than or equal to 1 over n. Here is less than 1 over n. The whole set belongs to the complement, extended complement of kn, and it is connected. This set is connected. Open disk is connected. So this set can, where is it? Yeah, this z. Let's put z0 here. Z0 here. Okay. This set z0 also belongs to it. Then what you get? This is this is a connect set, contains z0, and D is a component that contains z0. Then of course component totally contains this connect set. The connected component is the largest possible connect set containing this one fixed point. So this disk is contained in D. The disk is contained in D, right? Okay, so if D1 is the connected component D1 is a connected component of C infinity minus G that contains W, the same W, this W, this W. You have another connected component contains this W. Again, it is a smaller connected set. This D is the largest possible. Remember, because this is a subset. This is a subset of C infinity minus Kn. Where did I write? Yeah, here. It's a subset of C infinity minus Kn. So its component is supposed to be smaller than it. Okay? So it follows that D1 is a subset of D. D1 is a subset of D. All right? So we get that every component of C infinity, every component of C infinity minus Kn must contains a component of C infinity minus G. This is C infinity minus G. W, here W is not inside G. Definitely W has a connected component. We call this D1 as a connected component in it. Okay? All right. So we finished the whole verification why and how our constructed sequence of Kn satisfy these three conditions. Now let's see how do we use this sequence of a compact set to define the metric. Okay, so here G is the union of Kn, n from 1 to infinity. Kn is a sequence of compact set where each Kn is compact and Kn is a subset of an interior part of a Kn plus 1. Then we define a number between f and g, two functions which is a supremum of the distance of fz and gz, where z belongs to Kn, for all function f and g in Cg omega. Okay, so in this place, we do use that Kn is compact because we know that whenever here we use the compactness of Kn, the supremum is finite on compact sets. Supremum of a continuous function. Fg are continuous, so the distance between Fz and the Gz are continuous over compact set. Then this supremum is going to be the maximum, and it is compact. It is finite. If we do not have compactness of Kn, then you can still define the supremum, but it can be infinity, right? So if you can still define the supremum for this rho n, but this rho n might be infinity. Okay. So once you have this rho n for each Kn, we define rho of Fg to be sigma n from 1 to infinity 1/2 to nth power rho n Fg over 1 plus rho n Fg. And remember this trick. This is a very, very useful trick. This is a very, very useful trick. When you have a sequence, so here, sequence of bounded positive number, non-negative, let's not use positive, non-negative. When you have a sequence of bounded non-negative numbers, then the sigma 1/2 to nth power xn over 1 plus xn, and from 1 to infinity, converges. Okay, it is always convergent. We can use this to summarize and to construct a number related or determined by all xn. Okay, it converges, and let's call it x. And x is 0 if and only if all xn are 0. You want to get 0, then all xn should be 0. It's very, very, very important. Okay, so here this is a useful trick. You may use this later. And here we can, of course, this 1/2, you can replace it by 1/3, 3/4, whatever. This, we only use a condition 1/2 has ops value less than 1. It has ops value less than 1. You can replace it by any other smaller number less than 1. Positive, we need a positive. So whenever you have a positive number, positive smaller number, it is okay. Here 1/2 is the best choice, but I mean it's one of a good choice. There's no best or worst case to say. Okay. Okay, now let's see. With this definition, we're going to show that we define a metric. So let's see the lemma. If SD is a metric space, then mu of st defined by dst over 1 plus dst is also a metric on S. Okay, so you define two metrics on the same set, and we want to show that those two metrics are equivalent. What do we mean? They're two metrics are equivalent. They give the same open set. A set is open in SD if and only if it is open in S mu. SDS mu, the openness are equivalent. A sequence is a Cauchy sequence in SD if and only if it is a Cauchy sequence in S mu. So the limit are equivalent, the openness are equivalent. So whenever we have this, we will say they have the same topology. All the continuous function theory can be transformed from one to the other. All right? Okay. So as suggested in the textbook, you should prove this lemma by yourself to try it. Okay, so to show there's a, it is a metric, a function. Let's put D. From S cross S to R plus union 0 is a metric if it satisfies three conditions. One, xy is always greater than or equal to 0, and dxy is 0 if and only if x is 0, x is equal to y. And second, it's a symmetric. dxy is dyx for all xy in S, all xy in S. And third, the most important is a triangle inequality. The distance between xy plus the distance between zy is greater than or equal to the distance between xy. Okay, the triangle inequality. So you're going to show this for the mu st based on dst. D is a metric. You're going to show mu is also a metric. All right, and then you will get the relation between the open set and D and the mu. So do it. It may be the problem in the exam. So okay. All right. Assume you finish this proof. Sorry, not this. Assume you finish this proof. We will see the proposition 1.6. The CG omega with this rho is a metric space. Is a metric space. So basically, you are going to show that this is a metric. Rho Fg is a metric. Okay. So let's see this proof is short. Technically, there's nothing to prove if you already have the 1.5. So first, rho Fg is rho Gf. It's a symmetric. It's a symmetric property, symmetry. And the lemma 1.5 technically gave us the triangle inequality. So lemma 1.5 shows the triangle inequality. Triangle inequality. Of course, it's always positive, and equal to 0, it depends on the positive definite, positive definite. Okay, and another thing is that rho fg is equal to 0 will imply f is equal to g. Okay, the thing is that if f is not equal to g, there is a point z0 in G such that fz0 is not equal to gz0, right? Then we can see that there is a neighborhood U of z0 in G such that the distance, where is the definition of here? This one. This one. The distance between fz gz is going to be less than some delta for all z in U and the sum. Let's choose this delta. Delta we can choose it to be the 1/2 of distance fz0 and gz0. This is non-zero. We just pick up 1/2. It works. Okay, we don't need the sum delta. Let's make it specific. This one comes from the continuity of the function f. Okay, and then this implies there is a compact set. You see, there is a compact set. K. There is a compact set K inside the G such that this rho, this compact set, let's choose this, choose a compact set inside this U containing, whatever contain or not, this compact set inside U, of course, in G, such that the supremum of the distance fz and gz, z belong to K, this supremum is greater than 1/2 distance fz0 and gz0, right? And this K belong, by the second condition K, there is and Kn with K inside Kn, so the rho n fg will be greater than 1/2 the distance fz0 gz0. Okay, then rho fg is going to be greater than 0. So if there is a point so that fz0 is not equal to g0, in other words, if f is not equal to g, then the distance will be strictly greater than 0. Equivalently, if the distance between f and g is equal to 0, then f must be equal to g. This is equivalent to the fact that rho fg equal to 0 imply f equal to g. All right, so that's the positive definite proof. That's a positive definite proof. Okay, so that's the metric. But be careful, this metric actually depends on the choice of 1/2. Remember that we have this 1/2 selection. for a different smaller number, you can choose 1 over 3, 1 over 4, 1 over 5, 1 over 10, whatever smaller number. You will have different row, so you will have different matrix space. Okay, so we want to claim in the next lemma, we want to see that even though you have different matrix, so that's the remark. This matrix depends on this 1/2, the selection of 1/2, but the next result shows that the topology means open set. The topology of Cj omega is independent of 1/2. You choose whatever stuff, you will have the same open set. Okay? Same open set means in one topology, you say 2 elements are close. In another topology, those 2 elements are still close. But the distance, how close it is, distance is 1 or distance is 1/2, that's different. But we can still say they are close. Okay? So that's what we're going to prove in the next lemma. Okay? We finish this video now. Thank you.